the 2-unit/3 unit idea is the discs and the washers. But we can think about it in a different way. If we, instead of taking the slice perpendicular to the rotation, we take it parallel to the rotation. So let's have a look, random curve here. There's y equals function x, and we're going from A to B. So the slice, I'm going to rotate round the y-axis here, this section. So I'm taking it parallel to the rotation. Now if I rotate that slice, I now get a cylinder. Which it's easier to think of as a rectangular prism. Okay, so if you imagine cutting the cylinder and unravelling it. Okay. Now I can do that because the thickness, remember, we're going to take is approaching close to 0. So yes, in reality, that wouldn't be dead straight like a rectangular prism. It would be tapered out because one edge would be slightly bigger than the other one. Okay. But because we're taking it approaching 0, then as it approaches 0, they're going to be the same. So we can think of it as a rectangular prism. So the height of the rectangular prism will be the y value, but again we need it in terms of the thickness. So we'd have to rewrite that in terms of x. And the base is just going to be the circumference of the circle. So 2 pi, and the radius in this case is the x value. So the cross-sectional face is our rectangle, so length times breadth, 2 pi x times function x, and we get our volume element. And then it's a matter of summing up, and it's a bit like those, those, what do they call them, babushka dolls? You know what I mean? The Russian dolls, where you got one inside of the other, and they're all nesting in. And so that's sort of what we got here. We've got all these cylinders that are sitting inside each other, which would make up the volume of the shape. And so we get a different integral. It's x times function x, or 2 pi times x times function x. Now, we can't just quote that formula again. We've got to build it up. But it can make some of the integrals easier to do. Same question that we did the other day. So upside down parabola. And we were going to go around the x-axis. So this time I'm going to take the slice parallel instead of perpendicular. So if I was to rotate that, I'd get my cylinder, which I'm going to unwrap to be a rectangular prism. The thickness is delta y. Now, the actual height of my cylinder is going to be twice the x value here, because I'm going either side of the axis. So twice x. Making x the subject, I get 4 minus y to the power of a half. So we've got 2 lots of that. And the circumference will be 2 pi the radius. The radius is the y value in this case. So I get 2 pi y. So my area function, 2 pi y times 2, 4 minus y to the half. So I have my volume element. We're going to be summing, and it's the y values we're summing, so we're going from 0 to 4. 0 to 4. And so here's my integral to do. 4 pi the integral is 0 to 4 of y, 4 minus y to the half. So in this case, the other method probably is an easier integral. But just to show it does come out to be the same thing. Now I can do this, because also note, look what I've got. 0 to 4, the function's 4 minus y. So I'm going to use that idea where I can substitute in 4 minus y for y, and it'll be the same integral. If you're going integral 0 to a, function a minus x, same as function x. That's a bit easier to do now, because I can expand that out, add 1 to the power over power, and you should find we get the same answer that we got before. So 512 pi on 15. We've got a circle. We're going to rotate it around x equals 4. So there's our circle. Rotate x equals 4. So when we rotate a circle around a line, donut to the average man in the streets, mathematical name, torus. Donut. So I'm going to go around x equals 4. So my slice is vertical, and we'd end up with a cylinder. And this is now my wonderful attempt of drawing the torus.
Whoa.
Use your imaginations. That's a donut. No, torus. Not donut. Alright. Unwrap the slice, we get our rectangular prism. The thickness is in terms of x, so we want everything in terms of x. The height of my cylinder is going to be twice the y value here. Now, so I need to rewrite this. I'll get 2 lots of the square root of 4 minus x squared. Now the radius, we've got to be careful because we're not going around the axis, we're going around the line x equals 4, so it'll be 4 minus the x value. So we've got 2 pi 4 minus the x value. There's my area function. Element of volume, so delta V, there it is, sorry. Summing from minus 2 to 2, there's my integral. It actually is an incredibly easy integral. Because look what you do. I'm going to split it up into 2 integrals. And so 4 lots of the square root of 4 minus x squared, and then minus the x lots of the square root of 4 minus x squared. Well, look at what you got when we tidy it up. Square root of 4 minus x squared is... Right, so I can just do pi r squared. But look at the other one. X times the square root of 4 minus x squared. Odd function. Y equals x is odd. Y equals the square root of 4 minus x squared is even. Odd times even. So I know that integral equals 0. So, semicircle. So there's my 16 pi, half a pi r squared. That one turns out to be an odd function, so minus 0. We end up with, there we go, 32 pi squared. Let's give this cylindrical shells a go.